Okay, so let me read the problem out loud to you again. Hopefully you'll listen. And I do want to remind you that 99% of the time, 99% of the time, I'm not saying 100%, I'm not saying absolute, that you can rely on that last questions right there to help guide you to define your variables. Always, almost like always, almost. I said almost. So let's read carefully. A small plane leaves San Jose Airport and flies south to Los Angeles at 240 miles per hour. A jet leaves San Jose Airport 30 minutes later and follows the plane at 360 miles per hour. How long does it take the jet to overtake or to catch up to the small plane? Okay? Are you clear of that? All right. So, with that in mind, let's ask you a couple questions here. So we know that they're both trying to head towards LA. One plane, the small plane took off first. The jet took off later. But then the jet's trying to catch up to the small plane, right? Can you imagine that scenario? What do you think, as an observer from down below? At that point in time, you observed from the very first moment when the plane took off from San Jose Airport, and also 30 minutes later when the jet took off from the same airport. And then at that point in time in the sky where you see the jet caught up to the plane, what has to happen for that to happen? For the jet to catch up? Yes?
The jet has to be faster.
Oh, well, okay, so you see that already. But what can you say about the distance of the two objects at that point in time? Yes, Nicholas?
The distance has to be the same.
The distance have to be the same.
Yes.
Does it make sense for him to say that?
Yeah.
That the distance for you to catch up to someone, technically, if you're starting at the same point, you have to actually run the same distance in order for you to catch up. So let's pretend that this is San Jose Airport right here. The plane took off first. Right here, it's going slower, but the jet took off sometime later, right? But for the jet to catch up the plane, notice that for them to be side by side like that, distance of the two have to be the same. So that's the first thing that you need to remember about this case. The catching up case means that the two distances will have to be the same for the other object to catch up to the one that took off first. Is it absolutely clear about the distance between the two? Okay, good. You can actually sit down now.
Oh, cool.
And yeah. Thanks.
What the?
That was easy, right? Yeah, that's insane. Okay, now, that's easy. Now, here's the next one though. We also know that the jet took off 30 minutes later. Is that correct?
Yeah.
But you also recall that in the problem, the speed of each object is measured in what? Yes. Miles per hour. And do you see a lot of miles per hour, or do you see very little of miles per hour? Okay, so my word is this. I mean, if you see that case, do you still want to use 30 minutes, or would you like to convert that back into another unit? Is that okay for you to mix hours and minutes together? Yes or no? Raise your hand if you think you know the answer. Huh? Anyone here? Jennifer? Yes? So it's okay to mix the two together?
What do you mean by mix?
So notice that the speed is measured in an hour. But then there's that one part in the problem that says the jet took off 30 minutes later. That is a unit difference, right? So, Nolanda.
No, because they should be the same unit.
Okay, you're saying it should be the same unit. So how would you like to do this? Would you like to convert hours to minutes or minutes to hour? Okay, so let's convert that. Help me convert, Nolanda. How do you convert 30 minutes to hour? Okay, so in other words, you put the minutes over 60, right? And so what would that give you? 1/2, okay. 1/2 or 0.5 what? Hours. Thank you, have a seat. So another reminder about this is that whenever you see unit discrepancy in the problem, you gotta have uniform unit. If you see a lot of hours in there, convert it back to hours. Do not leave minutes and hour all mixed up together in the same problem. You gotta have the same unit to work with. Okay? All right. Since this problem concerned about distance and rate and time, can you also give me what is that formula that you normally use for involving those kind of units? You probably learned this in science as well. What kind of formula do we have here that involves distance and times and rate? Science? We use this a lot in science too. Actually, in real life. Do you remember that at all? The question is, since this problem involves time, rate, and distance, is there a particular formula that we want to use for this kind of problem? Going back out. Mel?
8 times time times distance.
Is that how it's defined? Christy?
Distance equals time.
Okay, thank you. You have a seat. Wait, tell me, is this new? You have seen this before. Distance equals rate times time. And don't forget, this one particular one right here is used to measure the distance or the rate or the time of one single object. How many objects do we have here? Two. We have the jets and we have the plane. So because of that, I need you to start thinking about solving the problem by using a what? What's the first thing we normally do when we start solving for this kind of problem? Can you help me define a variable, please? What do you want? Okay, so you're saying small plane, but then what are you really describing? X is the entire small plane? What are you trying to measure here for X? What is it about the small plane that you're trying to measure here in this case? Distance? Remember I told you that 99% of the time, the last question in the problem will guide you to your solution? I mean, guide you to your definition of your variable. So let's throw this back out to the audience here and see if you can actually give me that. What do you think I should define here for X? Yes?
Sine of the small plane.
Thank you. Is that true? That the time in the air? You don't want to start measuring when it's still on the ground, right? Is that correct? Okay, so I'm going to give you another chance here. So what do you think we should define? What else should we define?
The time in the air and the rest.
So what do you want me to write?
Y the time in the air.
Okay, thank you. Have a seat. Is this something that's new? Notice even though the questions only ask you about the jet's time, if you don't know the plane's time, you can't figure out the jet's time because they're actually tied in together, right? And once again, we declare two variables. One's for the plane, one's for the jet. Why is it a mixture problem? We have two objects once again. Just like any other problem from the past, we involve two things in the same problem. Okay, we need them to be separated because the jet's time is definitely going to be different from the plane's time. Now here's the part that I'm going to ask you on. This is all we have left. How can you use these two variables that I just defined and write our first equation that has to tie into the time part? Remember, we involved what here in this problem? We involved time, and we involved the speed, right? And other things. So since we just defined time for each object, the jet and the plane, how can you use these two variables to come up with our first equation that has to tie into time? What do you know about the time of the two from the problem? Anything from the problem that has to do with time, you want to actually drag it out and say, hey, yeah, this is the information about time, and I'm going to have to do something about this time. All right, so think about that. Remember this first question that I asked you before? What can you tell about the time of the jet and the plane with respect to each other? Even though you don't know the exact time in air, but what do you know about the jet and the plane? Come on. Anyone else? You said Jennifer?
Repeat that question again?
My question is, even though we don't know the exact time in the air for both objects, right? But there is something mentioned about time in the problem. can you use that information to write your first equation? Because we also declare, notice that the two variables also have to do with time. What do you notice about the time in the air of the jet versus the time in the air of the plane? Yes, Fatina.
The jet leaves 30 minutes after the small plane.
So how can you actually tie everything in based on that? Okay, Jennifer, go ahead.
Y plus x plus 0.5.
Okay. How did you get that? What do you think? If x represents a small plane, time in the air, is this actually correct? Let me just verify something. I'm not saying this is absolutely correct. Why? Which plane, or actually which object stays in the air longer? The small plane, right? Because it's actually left half an hour before the jet. Agree? But based on what you're saying here, that the jet time in air is actually half an hour more than the small plane. Ah, so how should we adjust this to make it work for our problem? Which objects spend less time in the air? How much less? So how do you adjust this to reflect that? Yes. Or instead of writing that, can we just go ahead and do this? Minus? Is that the same? Isn't the time in air of the small plane minus half an hour will be the jet's plane because it took off half an hour later? Yes or no? What do you think of that? Does it make sense? We clearly know that the jet took off half an hour later. That means it had less time. So if you have to compare x and y, this one is the bigger value, and this was the lesser value. And the difference between the two is exactly half, right? To make it clear, you see, you would do something like this. Is that correct? Small time, the time of small plane minus the jet's time should be half an hour, right? Because this one stayed in the air longer. How much longer? Half an hour longer. That's how we find a difference in time. Is that true? And notice that if we manipulate the variable, you get the same result. You add the y over here, move back to 0.5, and that's what we should have. Right? Right? So we all agree with that one. Right? Okay. So let's erase that for now. Next one. By the way, any question on that before I move on? Otherwise, I don't want you to get confused on how I obtain that particular function equation. Notice how once I start declaring a variable, I have to come up with my first equation right away using the variable I just declared. And since my variable has to do with time, I declare an equation that involves time. Is that the case? Has it been the case all this time? If you actually go back and review all the prompts that we've done so far, this is the case. Every time I declare my variables, I'm done declaring, I'm going to have an equation that kind of tie what I just declared right away. That's my first equation. Now, here's the second part. We know that the small plane travel at what rate of speed?
240.
240. Okay, so 240 miles per hour, right? This is the small plane. And we know that the jet here travel at 360 miles per hour. Now, why is it so important for us to have this thing written up here? We think we're just going to write it up for no apparent reason. You know we're going to have to use that. And why? You know that that particular one right there is going to help us obtain our second equation. How do we obtain it? This is what we know. First of all, what do you notice about, we already have this variable. This is representing the time, right? And this is the rate. If we take the rate times time, what do you get? The distance. We have the rate over here too, and we times it by the time. What do you get back?
Distance.
Ah, but what did I say about the distance of the two objects when the jet caught up to the plane?
That's the same.
Okay, so do you agree that for the small plane, the distance is defined as 240 miles per hour times it by the hour, which is x hours, right? Won't this give you the distance of the plane? Yes or no?
Yes.
Notice I'm using the direct formula. Over here, is it 360 times y? will that give you the distance of the jet? Yes or no?
Yes.
And what did we conclude about the distances of the two? So when you say they are the same, how do you write that as an equation? If the distance of this is the same thing as that, yes.
240x equals to 361.
Look at that. Is that true? That the distance covered by the plane should equal to the distance covered by the jet. And that's how the jet caught up to the plane. If the two distances are not the same, that means the jet is not there yet with the plane. Or maybe it's gone past it, right? It's either down here, up here, or it has to be the same in order to see the plane, side by side. Do you understand this particular one? And what's in it? The way that we verify? Look, won't this give you distance? Won't this give you distance? Distance, time, time, time. It has to work like that for you to write an equation. If you see any discrepancy between the units, you know it's not correct. Okay, now that we have our two equations, let's go ahead and box this. What's the next step after this? Raise your hand if you know. You should know right now. Yes, Justin?
Choose a method.
What method?
Substitution.
Okay, so which method should we choose this time?
Substitution.
Why?
It's not mine.
It's not line for ones, and we also know that isn't y has a name for it? Another way to represent y? And therefore, which equation should we substitute into the other one? What goes where? Is the red going to black or black going to red? Okay, so we know that y is x equals to 0.5, right? X equals to, y is x minus 0.5, right? So what do we do with that?
Plug in the
Yeah, right here, right? It goes straight into here. So if I rewrite the problem, it's going to look like this. 240x equals to 360 x minus 0.5. Raise your hand if you have any problem with that. This is substitution. It works because, hey, it's easy. What do we do now? What's that? Distributive property. Very good. So when we're using distributive property, we will have 360x. What is 360 times?
180
Okay. So you write minus or plus?
minus.
Minus. What do I do now?
Use.
Huh? Yes, Mark.
Combine the line terms.
Okay, which like term are you talking about? Okay, how do you combine like terms?
Subtract.
Yes, Dan. I know, but so tell me what to do.
Subtract 360.
Very good. Subtract 360x over because we want to put all the x's to one side, right? See that? So this is gone. What's 240x minus 360x?
Negative. Negative 120.
Negative 120x equals to negative 180. So we divide both by negative 120. X is 1.5 what? Hours. So we agree that x represents the small plane's time in air. Then how fast? I mean, what's the time that the jet stay in the air? 1 hour. Yeah. All you have to do is take that, plug it right here. 1.5 minus 0.5 is 1 hour. So the small plane is 1.5 hours, and the jet is exactly 1 hour. And if you don't believe me, do this. 240 times 1.5. Guess what? It's 360 miles. 360 times 1 is 360. So at that point in time, they're 360 miles from the base, but they are neck to neck with each other. And there it is. This is how we do it.
So it would take the jet 1 hour
To catch up. Exactly 1 hour later. Okay, so the plane spent 1.5 hours in the air, and at that time, when the pilot looked over, there it is, the jet's right there. 1.5 hours later. Okay? Any question on that in this problem?